Hello guys, and welcome to my first video. I'm still new to this whole YouTube / video editing thing, so please be patient and bear with me. I have a PhD in synthetic chemistry, and I'm very passionate about molecules, how they're made, and more specifically, the really exotic ones. I hope to make it my goal to bring some of these interesting molecules that are being designed and developed on a regular basis to the general public. A lot of this knowledge is locked into scientific papers and it's not readily available to the public for quite a variety of reasons. First, the terminology makes it very difficult for the average paper to be understood by a general audience. And second, that a lot of these papers are published in peer-reviewed journals which have paywalls, and as a result, a general audience cannot access these papers. I mean, look at this title. How many of these words can you understand? It's like a different language. Aromaticity, saturated rings, neutral aromatic, silicon, cyclobutane, what the heck? But anyway, today I want to show you a weird molecule that I came across when I was looking at the literature. So this is a very strange molecule because it contains a nickel atom inside a hexagonal ring of phosphorus atoms, which is very unusual for a nickel. Look at the structure. Look at how perfect that hexagon is. So just so that you know, the central atom in teal color, that's the nickel center, and those 6 orange atoms are the phosphorus atoms that are directly bound to the nickel. Now these phosphoruses are crucial because without them, the nickel cannot exist on its own, and it would otherwise aggregate into metallic nickel, which would not be what we want in this case. You can also see that there's these series of atoms all around the phosphoruses, and these are what we call the steric protecting groups. They're compounds or fragments that are attached to the binding atoms to stabilize the molecule, to prevent it from reacting with other things. Now I'm going to show you the structure using a space filling model, which in other words indicates how much space the actual atoms occupy. So you can see just how much volume those steric protecting groups occupy, which again, it's very crucial for allowing that nickel to exist as a single atom. You can see once again the phosphoruses in orange, and those are again quite protected in there. So the nickel again in teal is it's buried in there, which is the primary reason as to why this compound was able to be isolated in the first place. This molecule was reported surprisingly in a paper in 1992 by the group of Fenske, which was in Germany, and this got me really curious, so I started doing some digging. So there's around 3 papers related to this molecule. Here's that first paper in question from 1992. As we can see from the author list, Professor Fenske is among them, and if we scroll past the intro, we'll come across the reaction scheme that synthesizes the compound under discussion. So we have here, starting from 1 equivalent of nickel dichloride, which is a nickel 2 source, and if we react this with 2 equivalents of p-terbutyl phosphorane, which is a 3-membered ring, alongside a reducing agent, which is another trivalent, which in this case is a trivalent phosphine, we get this reagent to act as a reducing agent, in other words, an electron donor, and also as a halogen scavenger. So this is the reagent that takes the chlorides from the nickel and converts the metal into a nickel 0 source. This is done with concomitant formation of trimethylsilyl chloride, which then gives us the nickel 0 metal, which is trapped by the phosphorane, or the 2 equivalents of the phosphinidine. And this is done via a ring expansion from a 3-membered ring to a 6-membered ring, giving us the compound shown here. as well as by the crystal structure with the nickel in the center and the 6 phosphorus atoms in a hexagonal coordination mode. The compound's isolated in 30% yield, which may not be so good, but when you're a synthetic chemist and you're on the front lines of what's been feasible, I would say this is still a very good yield, and I would take 30% yield any day of the week if I was making these delicate compounds. Here's the second paper in question, which is a follow-up and was published by a different group in 1996. And they report a series of compounds that are related based on that hexagonal planar coordination environment. In this case, we feature nickel and palladium. And they also report an alternative procedure for making this compound. In this case, they take nickel dichloride and 6 equivalents of terbutyl phosphine dichloride, which is a phosphorus 3 source. And upon reduction with magnesium, which is a metal, or in this case, an alkaline earth metal, we remove magnesium dichloride, and those electrons go into the phosphinidines alongside the nickels, which form the hexagonal hexaphosphinidine, which again traps the nickel zero. Now, the authors failed to mention anything about yields in this paper, and unfortunately, even though it's in German, I can spare you the details and just show you that they also synthesized the antimony analog. And in this case, we have the crystal structure of the nickel with the hexantimony hexagon. And further down, they also talk about the palladium analog. Stay tuned for more interesting molecules which I have down the pipeline, and keep an eye out for the future videos. Until next time.